I welcome you all in the fourth lecture of week 1 of Mechanical Operations course, which is on Characterization of Collection of Particle part 1. In this particular lecture, I will discuss about the collection of particles, because for any product collection of particles or mixture of particles matters instead of a single particle. In a mixture of particles, particles are having a range of diameters. In other words, synthesis of a given diameter particle with fixed shape in large quantities is almost impossible. Therefore, to ascertain the properties such as surface area, porosity, specific surface area, shape factor, etc., of the system of particles, it is necessary that we should know the size and shape distribution of particles. In many cases, certain property of the mixture is to be controlled. This is done by tailoring the particle size distribution. So, the particles must be separated according to their size before using them for any industrial operation, since the process efficiency very much depends on particle size employed. If you remember the first lecture of this course, that is the introduction, where we have discussed that success and failure of the product depends on particle size. Therefore, to measure the particle size or to separate the particles according to their size is important for the industrial operations. For example, the effectiveness of catalyst particles is dependent on their surface area, which in turn depends on their size. In the combustion of solid fuels such as coal, uniformity of fuel bed is very crucial parameter. So, you see the size is important as far as any application or as far as any industrial application is concerned. Therefore, determination of particle size distribution is essential in many chemical processes such as crystallization, polymerization and precipitation, in which production quality depends on the measurement and control of PSD, that is particle size distribution. Particle size is determined by a number of methods, such as here if you see this table, in the first column we have PSD method, by which different method we can determine the particle size, and here I am having the particle size range measured by each method. So, here if I consider sieve analysis, it measured the particle size above 40 micrometer, gravity sedimentation 1 to 100 micrometer, and so on. We are having different methods. In this particular lecture, we discuss sieve analysis to measure the particle size distribution. So, from here onward, what is sieve analysis and how particle size distribution will be done using this, that we will discuss. So, the easiest method to determine PSD is sieve analysis, where powder is separated on sieves of different sizes. Thus, the PSD is defined in terms of discrete size ranges. For example, percentage of sample between 45 micrometer and 53 micrometer when sieves of these sizes are used. So, here you see it is collection of particle on particular sieve we can obtain. So, it comes under discrete analysis. So, here I am discussing the history of screening, where whatever we have used in past days, that I will show over here. So, man has used methods of screening to separate particles of raw earth even before screening was first recorded in the history. So, if you see this figure, it is the very old screen which I have also shown in introduction lecture. So, it is the first recorded reference of screening dates back to 150 BC, where Greeks and Romans described using crude sieves of woven horse hair for separating minerals and clays. So, if you consider this particular screen, it is made of horse hair. Nowadays, we use the screen made of metal. In the 50th century, Germans used first woven wire screens. These screens were stiff sheet screen that were shaken by hand. So, that is the history of a screen. Now, what is a screen and why what I am calling as a sieve? If you see this figure, from this figure you can understand very well that what is a screen. Here I am having this particular screen where we have the uniform opening at the base. So, the screening can be called as an open container, usually cylindrical with uniformly spaced opening at the base as shown in this figure. It at the base of it we have uniformly spaced openings. It is normally made of wire mesh cloth, the wire diameter and the interspacing between wires being accurately specified. So, depending upon this opening, the material which should be available over it or should be passed through it, that we have to consider. Therefore, if you see this figure, it has different screen. If you see these two screen, it has larger opening in comparison to this. So, larger particle can pass through this and a smaller particle can pass through this. Along with this, in this particular figure, we have another container which has no opening at the base. So, we call it as a pan. So, if you consider the screen, it has three basic component. First is the screen itself, second is the pan which is placed below to the screen, and third we have the cover which placed at the top of the screen, so that during operation fines should not take off from the system. And in this figure, if you see this particular component, it is basically called scoop to feed the material at the screen. So, the openings of a screen are commonly square, though rectangular opening are not unusual. The size of the square opening, that is the length of clear space between individual wire. If you see this figure, it has the opening as I have shown over here also. So, this particular square opening is called the aperture size of the screen. Therefore, depending on this particular size, the material which should be passed through it can be decided. And in this particular figure, you see here somewhere I am having the square opening and somewhere I am having the rectangular opening. This we used when we are dealing with needle kind of or rectangular kind of material. For example, if I want to screen the mica. So, screens are usually designated by their mesh number. What is mesh number? Mesh number indicates the number of apertures per linear length. For example, if I consider in a screen 10 square opening, so 10 would be the mesh number of that particular screen. So, how we define the opening of that? Suppose I am considering linear length as 1 centimeter and 10 mesh screen I am considering. So, 1 divided by 10, that is 0.1 centimeter minus the wire diameter would be the aperture size of the screen. So, therefore, higher would be the mesh number, smaller would be the aperture size of the screen, because length would be uniform, that is 1 centimeter. If I consider 100 mesh screen, 1 divided by 100. So, obviously aperture size will keep on decreasing as we increase the mesh number. So, this practice is followed in British standard screen, that we call BSS, American standard screen, ASTM and Taylor standard screens, German standard screen DIN 1171, etc. So, here what we have seen, the mesh number directly indicates the number of opening, and using this mesh number we can calculate how much would be the aperture size of a particular screen. Now, here I am showing one figure to show what is the effect of mesh number on aperture size. For example, if I consider the left figure, and in this figure you can see the aperture size is quite uniform. However, the right figure shows aperture size is not uniform. In the left figure, if I am considering this particular section where I am having 4 mesh, for example, from here to here, if I consider 1, 2, 3, 4 openings, so 4 mesh screen is there, for example. Here in the same length, if I am considering, so again 4, 1, 2, 3, 4 mesh screen. So, both are having 4 mesh screen. What is the difference between the two? If I consider only the mesh count, it means both should screen same material. But if you see the right figure, some openings are larger, some openings are smaller. So, obviously material will not be uniform. which will pass through this particular screen. However, if I consider the left screen, it has all material of uniform size which will be passed through it. So, this figure basically speaks about that instead of mesh number, do I have any other representation to show the screen? The answer is yes. Therefore, the Indian standard screens, that is ISS, however follow a different type of designation. For an ISS screen, the mesh number is equal to the aperture size expressed to the nearest decamicron, that is 0.01 mm. So, what Indian standard screen follow? That we define a screen in terms of aperture size, not as the mesh number. So, that is the mesh number is equal to its aperture size expressed to the nearest decamicron, that is 0.01 mm. Therefore, if I consider the screen of mesh number 50, the aperture size would be 50 into 0.01 mm, that is 0.5 mm, which we convert into microns, that would be 500 microns. So, in this case, as I am having increment in mesh number, I will have more aperture size. So, such a method of designation has a simplicity that aperture width is readily indicated from the mesh number. If I consider British standard or American standard, it is quite opposite. For example, if I having the more number of meshes or mesh number will increase, screen size will decrease. So, that is quite complicated to remember. However, in Indian screen, if I am having more number of meshes, it has more aperture size. So, it is easy to remember. So, standard test screens are usually made of phosphor, bronze wire, brass or mild steel wire are also sometimes used. It is always preferable to maintain a standard screen interval between successive test screen. An internationally accepted standard screen interval is 2 raised power 1 by 4, that is 1.189. So, here you see this particular interval we follow between two successive screen. However, sometimes we have some other standard also, but usually we have 2 raised power 1 by 4. This particular slide shows a Sieve's mesh chart, where you see here I am having the Sieve designation number as per Indian standard, and here corresponding opening is shown, and equivalent mesh number of ASTM, BSS and Taylor are shown over here. So, here you can see very well that as we decrease the mesh number from 570 to 70, in Indian standard screen aperture size will keep on decreasing. However, the mesh number will keep on increasing, that is just opposite to the Indian standard. So, here we have the C from 570 to 70, then again from 60 to 4, and correspond to 4 the value is 0.044. So, that is 44 microns. So, if you remember the previous slide, Sieve analysis gives the particle size distribution up to 40 microns or above to this. So, this screen vary from 570 to 4 mesh number. Now, what is Sieve analysis? Sieve analysis is basically done using a standard sieve shaker, in which screens of different sizes are arranged one over another. In this, test screens are stacked one above the other in the ascending order of their aperture size. If you see the topmost screen, it has the largest size because it has to retain the largest size particle and has to pass the particle lesser than this. So, therefore, the largest opening screen is placed at the top and finest opening screen should be placed at the bottom. Now, below the finest opening screen we should place the pan, and over the largest opening screen we should place the cover. So, the cover, different sizes screen and the pan will give the complete assembly of screen analysis. So, here how we do the screen analysis? Once this complete assembly is ready, weigh the feed, and that feed we keep at the topmost screen, and complete assembly is put into the shaker. This is basically the shaker here you see this particular assembly, it mechanically vibrates this particular set. So, as far as movement is concerned, it has gyratory motion, it has oscillatory motion, and along with that it has the vibratory motion. How the vibratory motion is done? If you see that topmost assembly, it has a hammer kind of structure which keeps on hammering this particular set from the top, so that the material which is clogged in between the screen, that should be passed through the screen. So, here I am having gyratory, oscillatory and vibratory motion when we put this screen into the shaker. So, after some time, the complete feed which we have put at the topmost screen should be distributed in this particular screen, and whatever is passed from the finest opening screen is collected at the pan. Therefore, in this schematic I have shown what will happen. So, if you see this particular screen, it has largest opening, and this particular screen has the smallest opening, and material is distributed according to their size. So, obviously topmost has the coarsest material, and below the finest we have the finest material which is collected at the pan. So, after a period of time, the vibration is stopped and the screens are disassembled. The material retained on each screen, including the material in the bottom pan, is weight. So, here if you see this, in this way we represent the data of particle size which we have obtained from different screen. So, here you see at 480 0 mass is available. However, at 400 we have M1 mass, and accordingly whatever mass is collected in different screen as well as pan, that we have noted down in this table. So, material that passes through the screen is called the minus material, which we also call as undersize, and the material that is retained on the screen we call it plus material, that is the oversize. So, if I am having this particular screen, whatever is available at the top, that we call oversize, and whatever is passed through it, that we call undersize or minus. So, while representing the data, we will use two signs, first is minus and second is plus. Minus shows material which is passed through the screen, and plus shows material which is retained on the screen. In this form, we represent the complete data. Like, if I consider this plus 480 mesh, it means material which has to be retained on it, that we have to represent over here, which is in this case is 0. It has size greater than 4.76. How this value we have obtained? By referring the standard Sieve chart. Therefore, if I consider the second data of this, that is minus 480 plus 400, here you see the material which is passed through 480 and retained on 400 mesh screen, we can write in this manner minus 480 plus 400, and its fraction is x1. What is this D average? How we calculate this D average is the arithmetic mean of size correspond to 480 and 400 mesh. The average size of particle D average is minus 400 plus 340 fraction, we have shown over here. Correspond to 400, the size is 4 mm, correspond to 340 mesh, we have size 3.353. If we take the arithmetic mean, the value 3.6765 mm would be the D average, or would be the size of material which is available at the screen, and whatever fraction is there, that is how we can compute this. That is very simple. Total mass which is available on that screen divided by the total mass which we have fed to the screen, topmost screen. Therefore, in this way we can represent the data of screen analysis, which includes mesh number, average size and mass fraction of the material. Considering this, we can derive the expression for a specific surface area of mixture of particle. For example, if I consider ith fraction, specific surface area can be denoted by this, that is SI equal to 6 Ni by rho D average I. This is a specific surface, that is surface area per unit mass of the mixture, And if you remember this particular expression, this we have discussed in lecture 3, where we were discussing specific surface ratio. Now, in this ith fraction I have considered d average I, and during this we have assumed that this particular fraction or similarly other fraction contains particles of same size, that is d average. So, surface area of ith fraction, how we can compute this? That is, we have denoted with capital Si. So, that would be small si, that is nothing but this, into total mass available in ith fraction. So, that is 6 Ni Mi by rho d average I, where Mi is the mass of ith fraction. Specific surface area of the mixture is, we have denoted this with Sm, it is equal to surface area of all fraction 1 to f divided by mass of the mixture, where I am considering total f fractions. So, this is the expression where this particular expression 6 Ni Mi by rho d average I we have written for each fraction, and similarly we have counted the mass of each fraction to calculate total mass. So, this m1 to mf can be represented by capital M. Now, if I consider small m1 and capital M, that we can write very well with x1, that we can represent with x1. So, finally, I am having this expression for f number of fraction. If we want to write this in a generalized form, that is Sm is equal to 6 by rho, because 6 by rho is common in all, because we are dealing with same material. So, density would be uniform, and here we have a summation where I move from 1 to f Ni xi by d average I. This is the expression for surface area of mixture of particles. In the similar line, we can derive the expression to calculate number of particles in a mixture. For example, if I am considering ith fraction, the number of particles in ith fraction denoted as Ni equal to mass of ith fraction divided by mass of one particle in a ith fraction. Further, mass of one particle in ith fraction can be written as density into volume of one particle in ith fraction. Numerically, Ni can be shown as Mi, that is mass available in ith fraction, divided by rho into Ai into d average I cube. D average I cube into A basically show the volume of a particle, where Ai is the volume shape factor. For this, you have to refer lecture 3 of this course. Now, for this particular fraction, we can calculate number of particles. So, total number of particles per unit mass of the mixture we can write as N divided by capital M, that is the total mass fed to the screen, and here we are having different fraction. For first fraction, it is M1 divided by rho A1 into d average 1 cube, and similarly we can represent for other fractions also, and here we have total f fraction. All these values will be divided by capital M. So, similarly, if you remember the last slide, M1 and capital M we have represented as x1. So, if I represent the expression in terms of mass fraction, that would be x1 divided by rho into A1 into d average 1 cube, and similarly we can represent for other fractions also. In generalized form, we can write 1 over rho and summation of f fraction, where I vary from 1 to f, and the expression is xi divided by ai into d average I cube. If I am considering all particle of same shape, then ai would be common. So, 1 over rho into a summation xi d average I cube, where I vary from 1 to f. This is the expression to calculate number of particles in the mixture for constant shape of all particles. So, once I am having this particle size distribution, I can calculate a specific surface area as well as number of particles per unit mass of the mixture, and considering these expression we will solve one problem in next lecture. Further, I am having measures to calculate the mean particle size of a mixture. If you remember the d average, what is d average? Is the particle size of a particular fraction. If I want to calculate the particle size of complete mixture, how we can calculate this? Now, once the number of particles in a mixture is known, one can compute the mean particle size of a mixture by following method. The first method is the arithmetic mean. We can compute the arithmetic mean of a mixture by this expression, that is summation Ni d average I divided by summation Ni. It means number of particle into average diameter of all fraction divided by number of particles in all fractions. If we write the expression of Ni, we can have the complete expression in this form. Once I resolve this, as all these value will be cancelled out, once I resolve it, the final expression of arithmetic mean would be summation I 1 to f xi d average I square divided by summation I 1 to f xi divided by d average I cube. So, this is the expression for arithmetic mean. In the similar line, we can have the quadratic mean. We also call it as the surface mean diameter. So, quadratic mean diameter, that is Ni d average I square divided by Ni for all fraction raised power 1 by 2. If I put the expression for Ni and further resolve it, we can have dq, that is quadratic mean, as summation I 1 to f xi over d average I divided by summation I 1 to f xi d average I cube raised power 1 by 2. Further, I am having the diameter as cubic mean, or we also call it volume mean diameter, that is dc, and here we have the expression Ni d average I cube divided by Ni power 1 over 3. Writing the expression of Ni and resolving it, the final expression I am having is summation I 1 to f xi divided by summation I 1 to f xi over d average I cube raised power 1 by 3. So, all these three methods are used to calculate the mean particle size of a mixture. And here I am having the summary of this lecture. The importance of particle size distribution and different methods for doing it was discussed in this lecture. Secondly, the designation and mesh number of Indian standard screens as well as other screens was described. Screen analysis and representation of screen analysis data in tabular form was discussed, and finally, based on PSD, that is particle size distribution, the expressions of specific surface area, number of particles and mean particle size of a mixture was derived. So, that is all for this lecture. Thank you.